So far we've studied normal form games and extensive form games, and these are ways to approach strategic games, strategic interactions. Evolutionary game theory is a subfield within game theory, which takes a very different approach. So what are evolutionary games? In evolutionary games, there is a changing population of players. So in a normal form game or an extensive form game, we have a set of players and they interact with each other, but in an evolutionary game, we have a population of players. And that population may change. The players are not acting strategically, they are actually not really decision makers. They are programmed to choose a certain way. So they are hardwired to follow a certain strategy. And each player may be hardwired to follow a different strategy. The payoffs they get in their interactions determine how fit they are, and then the more fit players reproduce and the less fit players die out. Strategies are inherited, so when players reproduce, the offspring inherit the same strategies, but there's a small chance of mutation, so there's always a chance that a new strategy would be introduced into the population. So players that follow strategies that are not as successful have lower payoffs, therefore lower fitness. They will eventually die out of the population, but the players that are more fit, that have higher payoffs, they will reproduce and their offspring will inherit the same strategies, so those strategies will become more frequent in the population. So what's an equilibrium in this kind of a game then? Well, a population that is stable would be an equilibrium population. What does that mean? It means that it can't be invaded by a small number of mutants, which means if we had a different strategy introduced into the population in some small numbers, that strategy would not be successful and wouldn't take over the population, so the population would be stable, would remain stable. There can be monomorphic equilibria, which means players are following pure strategies in their interactions, or polymorphic equilibria, in which case players are actually following mixed strategies in their interactions. This will become a lot more clear through a specific example. So let's look at a game. We have a population of players, and each player could follow the X strategy or the Y strategy. Now remember, the game we are looking at actually just describes the interaction that two players would have with each other when they meet, but this is not the game they are playing. This payoff matrix just describes their payoffs in interactions they have with each other. But these players are not choosing X or Y. They are either X players or they are Y players. When an X player meets an X player, they both get 2. That's their payoff. When a Y player meets a Y player, they both get 1. But when an X player meets a Y player, they both get 0. So again, this payoff matrix just describes the interaction that two players, X players or Y players, have with each other. It's not the game they actually play, because we are looking at an evolutionary game. So what we are really interested in is the population as a whole. So the questions we would want to ask are, if we had a population of X players, could they be invaded by a small number of Y players? Or if we had a population of all Y players, could they be invaded by a small number of X players? Because if they couldn't, that would mean that we have an equilibrium population, a stable population, or an evolutionarily stable population, as we say. So we'll find out in a minute how to actually answer that question using theory, using some mathematical reasoning. But a very interesting and fun way to try to find out whether a population is stable or not is to actually simulate that population and see what happens. And we can do that using a program which is called NetLogo. In NetLogo, we can actually set up a population and then describe the interaction that they have exactly the way I showed in the payoff matrix just a minute ago. So here we have 200 X players set up, they are green in this picture, and 40 Y players, they are red in this picture. And the interaction they have is exactly what was shown in the payoff matrix just earlier. So X against X gets the payoff A, which is set at 2. X against Y or Y against X will get 0. That's B and C here, and those are set to 0. And then if two Y players meet, they get D, which is set to 1. so that's a payoff of 1. Note that whenever we simulate an evolutionary game, the correspondence between the theoretical evolutionary game and the simulation is not perfect. So this is actually an implementation of the evolutionary game, and there are some small differences because we have to make some choices as we decide, for instance, when players reproduce. So here the reproduction score is set to 10, which means when a player reaches a payoff of 10, they reproduce, they have offspring. That will cost them some points as well. Also, if they reach a score of 0, they will actually die. Players will actually die out. Right now the random mutation variables are set to 0, so there's no random mutation at this point in this game. So what we would like to know is, as these players interact with each other, sometimes the X players will meet other X players, the green ones will meet green ones, sometimes they will meet red ones, which are the Y players, sometimes Y players will meet each other. As all of that happens randomly, how does this population evolve over time? So we could have these players move around, and as they move around, they meet each other and they interact. And here we can track their payoff. So here with the green line, we can see the average payoff of the X turtles, and the red line is the average payoff of the Y turtles. So we let this go, and what we see is that eventually the Y players basically die out. So the X players are dominant, which means, again, this small population of Y players was not able to invade the population of X players. And we could do this several times, and we would see that this was not just some random occurrence, but it seems to be pretty robust. Okay, now what happens? So that means that the population of X players seems to be stable. Would that be true for the population of Y players? So if we set this up so that we have a small number of X players in a larger population of Y players, so this is mostly red now, what would happen as they interact with each other? And we can see that now the Y players become dominant. So the X players basically seem to die out. And we could try that a few times too, and we will see that indeed the population of Y players is also stable. So we have, through simulation, found out that in fact the population of X players and the population of Y players would be stable. Could we show that mathematically? How would we be able to show that? So suppose that we have a population of X players, and they are invaded by a small proportion epsilon of Y players. Now we think of epsilon as some small proportion such as 1% maybe, or 2, or maybe 5, but definitely not a very large proportion, so we definitely don't think of it as half of the players turn into Y players. Okay, so we have a small population of Y players trying to invade this population of X players. To determine whether they would be successful, we would have to know what the expected payoff of an X player would be and what the expected payoff of a Y player would be. And then we could tell which one would be more successful in the long run. So for an X player, their expected payoff would be 2 times the probability that they meet another X player, because they get a payoff of 2 from an X to X meeting. So for an X player, the probability that they meet another X player is 1 minus epsilon. 2 times that, plus with probability epsilon they meet a Y player and get 0. So that means an expected payoff of 2 times 1 minus epsilon. For a Y player, with probability 1 minus epsilon, they meet an X player and they get 0. With probability epsilon, they meet a Y player and they get 1. So their expected payoff would be epsilon. So which player has a higher expected payoff? Well, as long as epsilon is less than 2/3, the X player has a higher expected payoff, and therefore a higher fitness, and therefore will reproduce more, and therefore the Y players will die out. So X is in fact an equilibrium, and it's a monomorphic equilibrium because all players are following a pure strategy, playing X. What about a population of Y players? Would they be invaded by a small proportion of X players? We can go through the same calculation. For a Y player, the expected payoff would be 1 minus epsilon times 1. That's the probability with which they meet another Y player. plus the probability with which they meet an x player, which is epsilon, times 0, and that would be 1 minus epsilon for an expected payoff. For an x player with probability 1 minus epsilon, they meet another x player, they meet a y player, which gives them a payoff of 0. With probability epsilon, they meet another x player, because remember, the proportion of x players in the population is epsilon. So with probability epsilon, they meet another x player, get 2, and that gives an expected payoff of 2 times epsilon. So which one is larger? Well, as long as epsilon is less than 1/3, the y player has a higher expected payoff, which means it has a higher fitness, and so it could not be invaded by a population of x players. So y is in fact a monomorphic equilibrium as well. That might be at first a little counterintuitive, because you might look at this payoff matrix and you might think, well, the x players clearly get a higher payoff with each other than the y players do with each other. But the fact is, if a population is almost all y, those x players have very small chance of running into another x player and enjoying that payoff of 2. Most of the time they will run into a y player and get 0, while the y players will run into another y player most of the time and get a payoff of 1. That's why they will be more successful. Note that if we were to look at this game as a normal form game and ask what the Nash equilibria are, they would be x, x, and y, y. Those would be the Nash equilibria. Now, this isn't, of course, a normal form game, because this is an evolutionary game, and we are just looking at the payoff matrix. But if we were to consider this payoff matrix as a normal form game, the Nash equilibria would be x, x, and y, y. And that's interesting, because the evolutionarily stable strategies are x and y. So is that a coincidence? It turns out that's not a coincidence, as we will see in just a minute. So what's the formal definition of an evolutionarily stable strategy then? An action A star is evolutionarily stable if there exists some small epsilon bar, such that for all epsilon smaller than this epsilon bar and all other actions B, the expected payoff for A star is higher than the expected payoff for this other strategy B in a population of A star players. So on the left hand side we have the expected payoff to A star. With probability 1 minus epsilon, an A star player runs into another A star player and gets U of A star, plus with probability epsilon, an A star player runs into a B player and gets U of A star B. And that would have to be greater than the payoff to a B player. So with probability 1 minus epsilon, this B player runs into an A star player and gets U of B A star. Plus with probability epsilon, it runs into another B player and gets U of B B. If A star is evolutionarily stable, then in fact A star is a Nash equilibrium of that payoff matrix, which describes the interaction of any two players. So this is the question I raised just a minute ago. What about the other way around? What if we know that A star is a Nash equilibrium? Can we conclude that it's evolutionarily stable? Well, almost. If A star is a strict Nash equilibrium, meaning strict Nash equilibrium, the payoffs for deviating would have to be strictly less than for following A star. If it's a strict Nash equilibrium, then A star is in fact evolutionarily stable. If it is not a strict Nash equilibrium, that means by definition there is some other strategy B that is also a best response to A star, which means the payoff of B against A star is exactly the same as the payoff of A star against A star. So U of B A star is exactly the same as U of A star, which means both A star and B do equally well against A star. So in a population of mostly A star players, they would both do equally well against A star. But then what determines evolutionary stability is how they do against the B players, that small proportion of B players. So then evolutionary stability would be equivalent to the payoff of A star being greater against a B player than the payoff of a B player against a B player. In other words, U of A star B is larger than U of B B. So that's the definition of evolutionary stability formally, and also the description of the relationship between evolutionary stability and the Nash equilibria in that payoff matrix that describes the interaction of any two players. So to summarize, an action is evolutionarily stable with respect to mutants using pure strategies if and only if A star is a Nash equilibrium, and for every action B that is also a best response against A star, U of A star B is larger than U of B B. In other words, A star does better against this strategy B than this strategy B does against itself. Okay, so that was for pure strategies. What about mixed strategies? We can define evolutionary stability exactly the same way for mixed strategies. So we can say that a mixed strategy alpha star is evolutionarily stable with respect to mutants using possibly mixed strategies if alpha star is a Nash equilibrium of the game that the normal form game that would result if we looked at the payoff matrix describing the interaction of any two players. And at the same time, for every mixed strategy beta that is also a best response to alpha star, the payoff to alpha star from interacting with beta would be larger than the payoff of beta interacting with beta. In other words, the expected utility of alpha star against beta is larger than the expected utility of beta against beta. So let's try to take a look at this in practice. The first interesting question that we could ask would be, is it possible that a strategy is an evolutionarily stable strategy with respect to pure strategies? In other words, no pure strategy can invade it, but it is not evolutionarily stable with respect to mixed strategies. In other words, there is actually a mixed strategy that could invade it. So take a look at this game and consider a population of X players. So we have almost all players X players, but then consider a small proportion of Y players trying to invade this population of X players. Would they be able to invade it? Well, let's think about it. The X players will mostly meet X players and get a payoff of 2. The Y players will also mostly meet X players, and when they do, they will get a payoff of 2, because Y against X gets a payoff of 2. Some of the time, a very small proportion of the time, they will run into Y players. So what happens when a Y player runs into a Y player? They get 0. What happens when an X player runs into a Y player? They get 1. Which means both the Y player and the X player get 2 when they run into an X player, but when they run into a Y player, the Y player gets 0 and the X player gets 1, which means the X player is doing better, it's more fit, and therefore X is evolutionarily stable and against the Y invaders. So that means the pure strategy Y would not be able to invade a population of X players. Well, could maybe a small population of Z players invade a population of X players? Let's think about that too. The Z players, most of the time will run into X players and get a payoff of 2, just as the X players do against another X player. How do they do against Z players? Well, the Z players, when they meet other Z players, get a payoff of 0, but the X players, when they run into a Z player, get a payoff of 1, which means, again, the X players are actually doing better than this invading Z player population, and therefore X is in fact stable against these Z invaders. So what that means is X cannot be invaded by either Y or Z, and so it would seem to be evolutionarily stable. Now, could it possibly be invaded by some mixed strategy? So could it possibly be invaded by players who mix between Y and Z? And let's just say that they mix between Y and Z with probability 1/2, 1/2. What happens then? Well, both Y and Z players get 2 against an X player. So again, when they meet an X player, the Y players, the Z players, the X players, they all get a payoff of 2. So there's no difference there. When an X player runs into player that mixes Y and Z with probabilities 1/2 and 1/2, what can they expect to get? Well, against Y they get 1, against Z they get 1, which means for a 50-50 mixture of Y and Z they still get 1. So the expected payoff of the X player against these invading mutant players would be 1. What about the payoff of the mixing Y and Z player against another player mixing Y and Z? Well, they will some of the time end up getting a payoff of 0, and some of the time they will end up getting a payoff of 3. Exactly 1/4 of the time they will get the YY payoff. Exactly 1/4 of the time they will get the YZ payoff. 1/4 of the time they will get the ZY payoff, and 1/4 of the time again they will get the ZZ payoff, which means on average they can expect 6/4 for an expected payoff, which is 1.5. So the expected payoff of this invading population of players mixing Y and Z 1/2 and 1/2, the expected payoff against another invader following the same mixed strategy is actually 1.5. What that means is that against the population of X players, the invaders as well as the X players get 2, but the invaders are actually doing better against each other than the X players are doing against these invaders. So that means actually these invaders will be more fit and will reproduce and will end up invading the population, which means X is actually not evolutionarily stable with respect to the 1/2 1/2 mixture of Y and Z. So it is actually possible that a strategy would be evolutionarily stable with respect to pure strategies, but not with respect to some mixed strategy. So let's take another look at polymorphic equilibrium, which involves mixed strategies. Here's, for instance, a game that has 2 pure strategy Nash equilibria. So if we were to look at this as a normal form game, we would say that DL and LD are pure strategy Nash equilibria. Of course, LD or DL can't be an evolutionarily stable strategy in any sense, because only L or D by themselves could be considered evolutionarily stable as pure strategies. We can't have a population of L, D, or DL players. We can only have a population of L players who are hardwired to play L, or a population of D players who are hardwired to play D. But what about mixed strategies? So what would be a mixed strategy equilibrium of this game? Playing L with probability 2/3 and D with probability 1/3 would in fact be a mixed strategy equilibrium of this game. And again, we are now looking at this as a normal form game. So that would be the mixed strategy Nash equilibrium. What about the evolutionary game? So we already know that an evolutionarily stable strategy would in fact have to be a mixed equilibrium of this game. So our candidate is now 2/3 L, 1/3 D. But for this alpha star strategy to be an evolutionarily stable strategy, we would also need that for any other mixed strategy beta, the expected payoff for alpha star against beta would have to be higher than for beta against beta. So let's just denote this strategy beta with P1 minus P, which means playing L with probability P, playing D with probability 1 minus P. Would it in fact be true that the expected payoff of this generic strategy beta would be lower against itself than the expected payoff of alpha star against this generic strategy beta? So let's try to calculate these. Okay, so with probability P, we play L. With probability 1 minus P, we play D. That's the strategy beta. Let's try to describe the expected payoff of this beta player against itself, another beta player. The expected payoff of a beta player against another beta player would be as follows. Some of the time they will both choose L, but then they get 0, so we don't have to worry about that. Some of the time they will both choose D and they will both get 0, and we don't have to worry about that either. But some of the time one will choose L, the other will choose D. So if the first chooses L and the second chooses D, the first player gets a payoff of 2. What's the probability that that happens? Well, with probability P it chooses L, the other player chooses D with probability 1 minus P. So with probability P times 1 minus P, the payoff is 2 against a beta player. And then some of the time with probability 1 minus P, the first player will choose D and the second player chooses L with probability P. So with that probability, 1 minus P times P, this player will get a payoff of 1 against this other beta player. In other words, the expected payoff of beta against beta is 2 times P times 1 minus P plus 1 minus P times P. Now let's take a look at the expected payoff of an alpha star player against a beta player. What would that look like? Well, again, if the alpha star player chooses L and the beta player also chooses L, the payoff would be 0. Also, if the alpha star player chooses D and the beta player chooses D, the payoff would be 0, so we don't have to worry about that. But if the alpha star player chooses L and the beta player chooses D, then this alpha star player will get 2. What's the probability that that happens? Well, the alpha star player chooses L with probability 2/3. So 2/3 times the probability that the beta player chooses D, which is 1 minus P, leads to a payoff of 2. So that gives us the first term, 2 times 2/3 times 1 minus P. And then with probability 1/3, the alpha star player chooses D, and then with probability P, the beta player chooses L. So with that probability 1/3 times P, this alpha star player will get 1. That gives us the second term, 1/3 P. And if we work through the math, we will see that overall that means an expected payoff of 4/3 minus P. So which one is larger? The payoff of the beta player against the beta player, or of the alpha star player against the beta player? So we can write down that as an inequality. On the left hand side we have the expected payoff of a beta player against a beta player. On the right hand side, 4/3 minus P, the expected payoff of an alpha star player against beta player. If we rearrange that inequality, so take everything to the right side so that there's 0 on the left side, actually we have a perfect square. On the right hand side we will have P minus 2/3 squared. So you should work that out to make sure that you see that that in fact is true, which means yes, actually the expected payoff of an alpha star player against a beta player will always be larger than the expected payoff of the beta player against itself, and that was for some generic beta, which means really for any mixed strategy this would be true. In other words, actually alpha star is an evolutionarily stable strategy.